strength versus density plots, where strength is the failure strength, which is defined differently whether it's a material uh, such as a metal or a polymer, which are ductile, or ceramics and glasses, which is a modulus of rupture, elastomers that are very high in ductility, and for composites, right? It's only tensile failure. So in this case, these are the way that strength versus density plots break into these kinds of bubbles according to forms, natural materials, polymers, composites, ceramics, and metals. And you have these different uh, guidelines for minimum mass design depending upon whether it's a tie rod, whether it's a column, whether it's a plane. So let's take the case where the slope is 2 over 3. So slope is 1.5 actually, when the index is 2 over 3. So in a situation such as here, the materials below this line would be eliminated from consideration. The materials above this line would be in the running. So most steels would be eliminated from consideration. But if you end up choosing a shape made from steel, where the shape efficiency factor is 10, so that phi square would be 100, it turns out that it allows for the same material to be used into this strength limited design by just making a different shape. So the new material index goes from sigma to the power 2 by 3 divided by rho to a way in which those 5 different shape factors that we came across, they could be substituted in over here, okay, along within the index of 2 by 3, and that would be the modified shape index. If you go through rearranging terms, you basically can use the same plot of strength versus density and just divide by phi square to account for different variations in shape. So the new material would have a modified strength of sigma over phi square, a modified density of rho over phi square. So if phi was 10, then you basically go from about 100 megapascals to about 10 megapascals in strength. Sorry, 1 megapascal in strength, roughly over here. And so you go above the line. At the same time, the density of the material goes down to below 0.1. Okay, somewhere around here. 0.8, roughly. 0.08. So basically, in the realm of foams, polymer foams is where the new shaped steel becomes effective as a material with a new shape. So this is a new material with modified sigma and rho attributes. This is another example of how we take the shape factor derivations for various shapes and combine the shape efficiency factors for different materials and go back to the material indices that we looked at before and the property charts that we looked before. And now we can begin to use EduPack. We can use the charts that were there in the text and so on, and look at this combined choices of shape and material to come up with competitive alternatives for a set of loading constraints. So to summarize, the shape factor is dimensionless because it's a ratio of stiffness for a new shape relative to the reference shape, or the failure strength for a new shape relative to the reference shape. So it's dimensionless, it's just a number. It is relative to a shape. So if for the same shape, you will have the same shape efficiency factor, right? Provided the areas are kept constant relative to the cross-sectional area. So that's another attribute to pay attention to. In the next class, let's look at deriving material indices and see how they are used when you account for not only the material type but also the shape. We will also look at ways in which we establish that there is a limit to how much you can shape a material. One example of looking at it is you can only make a piece of wood, so thin, after which it cannot be converted into shape. Same thing in terms of how thin you can draw a wire from a particular material before it fails. So, in a similar manner, we will look at deriving these material indices and also looking for ways in which the upper bounds for different materials, shape efficiency factors, are established or estimated. So, these are from chapters 9 and 10 from your book. I'll see you in the next class.